So some terminology we're going to need as we continue through Mod 5. The first term that I see here is a polynomial. Now that's a lot of junk here, okay? But if we, I can zoom in slightly. If we look at how those things are, some things to be thinking of. The x's are just in descending order. So n is your highest power. The coefficients can be any real number. So those a's are just indicating, hey, I'm the a that's stuck on n, the x to the n. Hey, I'm the a that's stuck on one lower, all the way down to our constant a sub 0. So they, the coefficients themselves, all of our a's have to be any real number. They can be fractions, decimals, percents, square roots. If it's on the real number line, they can be those numbers. But we have to be very careful because our powers, for it to be considered a polynomial, the powers must be whole numbers. What are whole numbers? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so those are whole number powers. So that's kind of what makes a polynomial a polynomial. Okay. Now, some examples of polynomials. 4x squared minus 1/2 x plus 7. That's a polynomial. So our quadratics, our linear functions, are polynomials. If you looked at the 7 functions, the ones that are polynomials, constants, identities, quadratics, cubics, those 4 fall into the polynomial category as long as their coefficients are real numbers and their powers are whole numbers. They are considered in our polynomial family. Those parent functions, constant, identity, quadratic, and cubic, are the most simple version of these things. These functions might have more junk to it. So yesterday when we were talking about those cubics, yes, this is going to be generally looking like a cubic. It's going to have one arm up and one arm down, but every time we add an extra term to the polynomial, we screw it up a little bit. We might add bumps to it. We might add flips to it and things to it. So what this does, this section starts to look at more complicated versions of those parent functions, okay? Just like before, the roots are where that function equals 0. So factoring is going to be our key here. We will explore more how to find the actual roots if it is a complicated function as we go through this next few lessons. So factoring is really the way to go. I'll remind you some of the rules of factors when it's going to happen, okay? The degree of a polynomial is just that highest power, that n. So, you know, for here, the degree of this polynomial is 2. The degree of this polynomial is 3. The degree is going to help us determine what the n's are doing. Are they pointing both up, both down, one up, one down, to the left, to the right, all those different things. So the degree really determines how our n behavior looks. It really determines how our n behavior looks. So that leads us then to end behavior. Okay, so let's talk about this section because there's a lot of junk there. Okay. Let's focus on these ones. So let's focus on if our degree is even. If our degree is even, let's think about one that we know right now, a quadratic. A quadratic is an example of this. Its degree is even. If the a that's touching it is negative, so that just means if the front coefficient is negative. So the front coefficient, if I could spell. So this is if the front coefficient is negative. this means the front coefficient is positive. Then the left end has to go up, and so will the right end if you have an even degree polynomial with the front coefficient being positive. The left end and the right end will always go up. Now let's talk about this notation. Do you see how the left end is always x is going to negative infinity? That is always how you move across the graph to the left. So you notice none of those change. If you need to move to the graphic to the right, all of them, the x's will always go to positive infinity. So you don't really have to think about that. If I need you to describe how is it going to the left, you always say x is going to negative infinity. If I say x is how we go to the right, you always get to say x is going to positive infinity. So that doesn't change. The thing that changes, you might notice, are the y's. Where are the y's going? If our front coefficient on an even degree polynomial is positive, both ends point upward, just like our parabola. If our coefficient is negative, both ends point downward or go to negative infinity. See how our y's are going down to negative infinity. That's what it will look like. Now let's talk about this side, an odd degree polynomial. Our cubic is a perfect example. If the front is positive, the left end goes down and the right end goes up. We know that's what happens to a cubic. Remember, our cubic goes whoop, left end down, right end up. That's exactly what happens to any odd power or odd degree polynomial where the front coefficient is positive. So all that front coefficient being negative does is it flips it upside down. So if, that's a perfect example, if this is 3x cubed. Left end's going to go right, or the left end's going to go down, the right end's going to go up. But if we have f of x equals negative 2x to the fifth, our degree is 5, it's odd, there's a negative coefficient touching it, I don't care even what the other stuff is, but the left end's going to go up now and the right end's going to go down. It's going to go flip it. So let me give you an example of each. Now, I'm not writing the whole polynomial. I'm just writing that first term, that highest powered term. So if this is 7x to the fourth, both ends are going to be pointing up. If our polynomial starts with negative x to the sixth, both ends are pointing down. Okay, so this is just a way to categorize what the end behavior is doing. If we have a polynomial with even degree, both ends will either point up or point down. If the front coefficient is positive, it points up, negative points down. If our polynomial has odd degree, 3, 5, 7, 9, 11, the left end will always go down and the right end goes up if our front coefficient is positive. If our front coefficient is negative, it flip-flops them. So the left end goes up, the right end goes down. Could you change this little word right here? That's the word down. When I was typing this, they were all starting to blend together. Okay. So let me make sure every one of them is right. That's down, that's up, that's up, that's down. Yeah, okay, now that's correct. So in the bottom there's just a general picture of a function that kind of fits that category. This one would have been of even degree with a positive coefficient, with a negative coefficient. These ones would have been of odd degree. This one with a positive coefficient, this one with a negative coefficient. So what this is going to allow us to do is it's going to allow us to kind of know where those ends head, so then we can draw some very quick general pictures. Just like in the last lesson, when we were starting to learn what those parent functions were doing, and we were drawing them a little quicker than we've ever done before, that's what this is going to allow us to do. Now, iMath does talk about Where is a function positive or negative, or what are the intervals where a function is positive or negative? If a function is positive, remember, when I'm talking about the function values, I'm talking about the heights of my function. That means the heights of my function are above the x-axis. So a function is positive if it's above the x-axis. A function is negative if the graph of the function is below the x-axis. So this quadratic I've drawn here, I have shown in red where our function is positive, and in blue where our function is negative. Now let's put some actual mathematics to it, okay? So we can say that our function is positive. That's just a shortcut way to say our function is bigger than 0. Our function is positive. Now, let's think about what x values where that happens. That section of the graph and that section of the graph. So how do we put that? Well, when x goes from negative infinity up to, but not including negative 2, it's positive. And also when x goes from 2 to infinity. So those are the x values that will give me a height that's positive. Our function is less than 0 in that middle blue section. So when x is anywhere between negative 2 and positive 2, and f of x equals 0 when x equals negative 2 or x equals positive 2. So a function is clearly positive or negative if the function is above the x-axis, it will be positive. If a function's below the x-axis, it will be negative. If a function touches the x-axis, then that's where the function is equal to 0. So this is where the function's greater than 0, less than 0, equal to 0, okay? So the equal to 0 are just usually individual points. Some functions, I mean, might travel across it like that, but yes.
For the blue or like below 0, why did they, maybe I'm just not looking right, but why did the infinity disappear?
Oh, let me show you, okay. So our function is below the x-axis. Think of a shadow. If it put a shadow here, only when the x values are between negative 2 and positive 2. So these are referring not to the y values. That's what the y values are greater than 0, as far to the left and as far to the right that I want to go. The function is negative in this little bump here only. So only from this value to this value. And then our function equals 0 exactly at those values. So it's just a matter of pulling apart what is the function's height, what are the x values where that happens. Okay. So now let's go to an example. So it says we have this function, x plus 1 times x minus 3 squared. Now, I want to prove to you that that's a polynomial. Just a second, I need to multiply it out. I didn't do that ahead of time. I should have done that, but I didn't think about it. If we were to multiply it out, it will look more like a polynomial. So let's just take a minute, and I'm going to show you, hopefully. This is an example of a polynomial. If you were to multiply it out, you get x cubed minus 5x squared plus 3x minus 9, okay? Now, if you also just look at our x's alone, we've got an x on a squared. So technically, our lead term, I'm going to abbreviate that LT, and I'll be using that more as we go through this process, is x times x squared. That's how we got that x cubed we see right there, okay? So if you were to actually FOIL the x minus 3 times x minus 3 is x squared minus 6x plus 9, and then you multiplied it by x plus 1, and you did that whole long multiplication, combined like terms, you get x cubed minus 5x squared plus 3x minus 9, which is a perfect example of a polynomial, okay? This is a polynomial with degree 3. So I'm going to say n is 3. So the degree of this polynomial is 3. Okay. Now, finding the x-intercepts or the zeros, remember, is just setting the function equal to 0. Now, what's really great about this particular one is they have done so much of the work for us. They've made our life really easy because of the fact that they have put it in factored form. So that's awesome. Factored form is our favorite when it comes to finding the zeros or the x-intercepts. So then you just rip it apart, set each version equal to 0. The square root of 0 is 0, so you don't even need to really include the square there. You're always going to get 3 no matter what you do for that one. And this one, you're going to get negative 1. So in that graph, like we knew up above, where it hit negative 2 and positive 2, we know the only spots that this particular function hits the x-axis is at negative 1 and 3. Okay. On a number line, let's highlight where f is positive and negative. So if we were just concerned about the x's, we're only concerned about the x's at this particular moment. We know that it hits 0 at negative 1 and 3. Because this is an odd function, I'm just going to kind of draw a very simplified version, okay? So don't expect that this is anything great, but this will kind of point you in the right direction. In that big old chart where there was all those little arrows, we said that if the degree is odd and our front coefficient is positive, the left goes down and the right goes up. Let me say that again. If we know that it's an odd function where our degree is odd, but our front coefficient is positive, the left always goes down and the right always goes up. We said a function that is below the x-axis is considered negative, and a function that is above the x-axis is considered positive, right? So we know, let's color in kind of the same thing I did before. This side is under, so let's keep it blue because it's got to go down. This side has to go up, so let's color it in red. Now, let's contemplate the part that's kind of weird for this one is this middle section. So we were down here. So we either have to stay here and go like this and then keep going up, or we have to go up like this and then keep going up. It's got to be one of those because we only hit, remember, the x-axis in 2 places. So we either have a bump down here, or we have a bump, I'm sorry, I didn't do that very good, but, or we have a bump that's above. We either have a bump above or below. So the only one that I'm questioning is what is happening in that center section. So here's how you check. If I plug in 0 to our original function, 0 is any number. It could be any number between negative 1 and 3. Pick a number. I like plugging in zeros. Zeros are nice to plug in. If I plug in 0, I get 1 times negative 3 squared, or positive 9. A positive implies that my function is above the x-axis. It has a height more than 0. So this section has to be red. Okay. So that function has to be above the x-axis. Okay. Now let's actually put it from that one-dimensional thinking. Let's take that and throw it on our graph. So on our graph paper, please hit negative 1 and 3. We know that. We know that the left end was going down and the right end is going up. Now, I could probably make more of a curve to that, but I don't care. See it, how it says the word rough sketch? That means do what you got to do. Okay. And then we know that this section has to be somehow like that. Okay. And we know if we plugged in 0, we got 9. So we got a point. So at 0, let's hit 9. So we need to at least have done something like that. Okay. Now, in a pre-calc class, we do not have a super effective way to find out how high or how low those bumps go. So you only really have the tool of plug in some points and see. There's a chance this bump gets a little bit higher even. I don't care. You're not sitting in a calculus class. You don't have the things you need yet. So that's why many of these will say, give us a rough sketch. Okay. Now, some things that happened. Let's look at our function one more time. And let's analyze some stuff. Our lead term was x cubed, which was implying that the left end goes down, the right end goes up. Okay. Highest power is our n is 3. Okay. Do you see how this thing here had an even power on it, had a square on it? What happens is anytime we have a factor that repeats an even number of times, that factor will always provide in the graph what I call a bounce. This factor is a through. As I can't spell ever. This factor is a through, and this factor is a bounce. So I went through -1, but I bounced at 3. Think of a bouncy ball bouncing off the floor. So that is another tool that we can use to help us draw graphs that are kind of accurate, but not completely. Okay. So that's a little bit more as we go through this, and I will give you some, more information as we go. Now, part D says, what would be the difference between f of x and h of x if we threw a 2 in front? All that 2 is going to do is stretch up the heights. So remember that 0 value? Instead of getting 9, we would get 18. So it would make, it's still going to go down. It's still going to go up more rapidly, but who cares? But this bump is going to be very high. Changes the height of the graph by a factor of 2. I don't know. Now, E, think about what a -2 is going to do. It's going to stretch it and flip it. It's going to stretch it and flip it. That f of 0 now is -18. This time, the left end is going to go up, the right end is going to go down, and this part's going to bounce. So it takes and it flips it and stretches it all at the same time. So don't be overwhelmed yet. As we go through, I'm going to pull out more and more functions and show you how to graph them very quickly and easily. We don't care about graphing super fast. We care about, yes. Yeah. Oh, this is lead term. So that is the term with the highest power. The term with the highest power gives us super amounts of information about what is the graph end behavior, what is the graph's direction. So that lead term, that term with that highest power, is really, really important as we go through this process. Everybody good with C, D, and E? Again, we're going to keep doing this, but let's take a look at our last question in this investigation. Power functions are given there. Now, a power function is more of our basic function. It is a power function is f of x equals x. It can have whatever you want there. x to the n, as long as it's a real number. Okay, so you only have one term. So that is some of the ones we did yesterday when we were talking about our parent functions. The power functions are constant, identity, quadratic, and cubic. We're going to explore what happens when that n is a whole number. It looks like that polynomial. What if it's a fraction? What if it's negative? We'll explore more types of power functions as we go. But these are types that are the simplest types of polynomial power functions, okay? So what do we know about the n behavior? Well, f of x, x cubed, g of x equals x to the fifth, both are power functions or polynomials with that odd power. So for these, the left end is going down and the right end is going up. Okay. Now, how do we write that correctly? Okay, we need to write that more formally, more mathematically. This will help you if you ever take a calculus class. Left end down, that means x is going to the left, the y is going down to negative infinity. X is going to the right, y is going up to positive infinity. Okay? And we know that because those are odd degree polynomials or odd degree power functions. So if you have a positive odd degree, you then get the left end goes down and the right end goes up. The ones that go together also are h of x and j of x. Those are both even degree polynomials. Both ends like a quadratic point upward. So the left is going to go up, the right is going to go up. They're both going to go up. Now let's write that more formally. How do you say mathematically that left has gone up and that right has gone up? Left is always x goes to negative infinity. The y is going up, that's positive infinity. X is going to the right, that's always positive infinity. Y is going up, positive infinity. Okay, so that is just clarifying that any even power, the ends always act the same on a polynomial or a power function that has an even whole number power. Every odd power function with an odd power that's positive will always do the same thing. Left goes down, right goes up. Both goes up for an even. One goes up, one goes down for an odd. And you just got to get used to that. Okay. What happens if we stick a -2 coefficients on these functions? We should expect that the ends flip upside down. So let's take our f of x and stick a -2 in front. Let's take our g of x and stick a -2 in front. This time our left will go up and our right will go down. This time our left will go up and our right will go down. Now let's write that a little more formally. So x goes to the left and x goes to the right, always the same thing. We don't have to worry about that. Going to the left for an x is negative infinity, going to the right is positive infinity. But this time our y value is going up. This time our y value is going down. Let's take our h and j and stick a -2 in front. So if we have -2x squared or -2x to the 8th. Think about our quadratic. Normally both of our arms or ends go upward. Now that's going to flip it upside down. So our left is going to go down. Our right is going to go down. Now you can throw these into Desmos and look, well, what just happened? So our left is going to go down, our right is going to go down. So this would mean that our x goes to the left, our x goes to the right. Always the same thing, that never changes. What might change are the y's. To indicate that your y's are going down, your y is going to negative infinity, a height of negative infinity. So y goes to negative infinity, y goes to negative infinity. So an even function, the y's always match. An odd function, they're always opposites. An odd degree function, the ends are always going in opposite direction. An even function, the ends are going in the same direction. Okay? So now, at this time, I would like to open up some iMath stuff. Do we have any questions about this before we say goodbye about this stuff? Yes. Yeah. So I will leave it there. As soon as you're finished, please turn in 5.5 day 1 investigation. We are now done with it. And then if you could open up your iMath, we're going to do some iMath together. Open up your iMath, we're going to do some iMath together. Please don't forget, you have a quiz tomorrow over that first page of the 5.3 day 2 investigation, I think it might have been, those parent functions. You have to tell me the parent functions. It looks just like that first page. So if you want to take a look at that first page, please study that quiz tomorrow, okay? If for some reason you're not going to be here tomorrow, please make arrangements for me as to when you can do that for me. Okay, so now let's go into iMath. And if you go to your calendar, you will see that on Sunday, there are some homework problems that are due. You have 3 homeworks that are due on Sunday. At this time, could we open up 5.3 day 1? That's the second one on the list. And can we look at some of the questions there? Okay. 5.3 transformations day 1. If we could look at some of these together, okay. I really want to focus on 10 and 11 because that's where some people were struggling. So I would like to open up problem number 10. Okay. Let me get kind of a sheet of paper here so I can show you some stuff. So if we look at this function, you can see that the graph of function f is given. It has domain from 0 to 2. See how the x values go from 0 to 2. I can't draw on it, but anyway, and the y values go from 0 to 1. Okay. Now it says to express the following in interval notation. And so part A, they have already given us the answer. It's right there written. The domain in brackets is 0 to 2. And our range is 0 to 1. Okay. Now, let's talk about B. B, we have added 2 on the outside of the function. Do you remember what does that do to our function? Makes it go up 2. So we have not changed the domain. We haven't touched the x, so it's still 0 to 2. But we have lifted that function. So we have to take our range and we have to add 2 to both of those because it's gone up higher now. So instead of from 0 to 1, add 2 to both of those. So that would go from 2 to 3. think about if it's on the outside, it changes your range. If it's on the inside, it changes your domain. Let's now go to C. A 2 on the outside of the function, it's on the outside of the function, it's going to change our range. So our domain is still 0 to 2. Let's throw that in there. But how does it change our range? It takes those original values, multiplies them by 2. So if I multiply 0 by 2, it's still at 0. But if I multiply 1 by 2, now it's up to 2. So our range goes from 0 to 2. Now let's take a look at D. D has something on the outside of the function. We have subtracted 1. That subtracts 1 from the range values. So the domain hasn't changed. But our range values, that 0 and 1, each have to go down by 1. So that's going to be -1 to 0. Let's look at E. There is a negative on the outside of the function. Anything on the outside of the function changes the range. So our domain is still going to be 0 to 2. But our range, now, you have to go in least to greatest order. If I multiply the original range, which was 0 and 1, by -1, I get 0 and -1. Is that in least to greatest order? 0 to -1? No. So it has to be changed from -1 to 0. Think about our function, which went from 0 to 1, got flipped over. Now it goes least to greatest -1 to 0. Now, for the first time, we have something that has changed our domain. What does it do when we add 2 on the inside of the function? 2 to the left. So we're going to take that original domain, that 0 to 2, and we're going to subtract 2 off of each. You have to do the opposite of what you see there. So if I subtract 2 from 0, I get -2. If I subtract 2 from 2, I get 0. That would move it to the left 2. -2 to 0. Nothing is on the outside to change the range. So our range is still 0 to 1. And you should be using brackets on all of these. Let's look at G. So on the inside, we've subtracted. What does that do? It goes to the right one. So we have to add 1 to our original domain of 0 to 2. So now it's going to become 1 to 3. That would move it, shift it to the right one. Our range is still going to be 0 to 1. Nothing has changed that. Let's take a look at B. We have to multiply our domain by -1. If we want to multiply our domain by -1, it was 0 to 2. It's going to become 0 to -2, which doesn't go. See how it flips it across the y? So that's why our domain becomes -2 to 0. Our range has not been affected, so it's still 0 to 1. Last one. This particular one has something on the inside, something on the outside. We have to adjust both. The plus one, we've discussed this already. When you add 1, it moves to the left. So let's take our domain, which was 0 to 2, subtract 1 from each. We get -1 to 1. Our range has a plus 1. We get to do exactly what we did. We can just add 1 to our range. Our original range was 0 to 1. If you add 1 to both of those, you get 1 to 2. So that is a little bit about domain and range and how those things we talked about change the domain and range of the original. Okay. Everybody good with that? We don't have much time, but let's do as much as we can of question 11 together, okay? So we have a function. Let's write down the original domain that they have given us of g. The domain of g they said is -2 to 1, which you can tell from the graph, and the range goes from -1 to 1.5. So that one's so much like the other. Let's see, I believe there's one that's kind of a word problem. I'm sorry, let's do 12 instead. Let's do 12 instead. It says the function f has a domain of 0 to 4 and a range of 0 to 3. Start by sketching a potential graph. We don't have time. We're not going to draw a graph, but you can if you want, you know what I mean, from 0 to 4 and 0 to 3, you know, it can be anything like that. I don't know. Okay. Has to hit a height of 3. It has to go from 0 to 4. I know. There's the graph. Okay. Suppose that g is defined as g of x equals f of x plus 6. Determine the domain and range. It's exactly the same thing. So if we add 6, that only changes our range. So now instead of going from 0 to 3, pick up both of those and lift them up 6. So the domain is still going to be 0 to 4. Our range, though, adds 6 to both of those. So it's going to be from 6 to 9. If you put a 3 in front of the function, it's going to stretch. Instead of going from 0 to 3, it's going to go from 0 now to 9. So the domain hasn't been affected, still 0 to 4. But our range now goes, if you multiply by 3, you get 0 to 9. C is going to take our function and flip it down here. So the domain doesn't change. Nothing's on the inside by our x. So it's still going to be 0 to 4. But our range now is going to go from -3 to 0. And then lastly here, how would the function change if we put a +4 on the inside? It would move it to the left. So we have to change the domain to go from -4 to 0. Just subtract 4 from both of those things. Our range would not be affected. It would be 0 to 3. You don't need to draw a little graph, but you can. You can make any sort of little graph to go with that. So don't forget, you have 3 homeworks due on Sunday. You have a quiz tomorrow. If you're not going to be here, let me know. It's going to be a very quick quiz so that we can make sure you get that done. So there you go.